Okay, great. So welcome everybody to this talk of the Israeli Algorithmic Game Theory seminar. This week we are delighted to have Shiri from Weizmann Institute talking about the communication complexity of payment computation. So welcome, Shiri.
Okay, so I'm going to talk today about the communication complexity of payment computation. This is joint work with my advisor, Shachar Dubzhinsky. And in order to present the question formally, I need to set up some definitions and notations. So I'm going to introduce the model of communication complexity, where we assume that each player holds a subset of the input, and we wish to compute some deterministic function on the shared input of all the players. And the question we're interested at is how many bits do the players need to exchange in order to compute the function? And we denote this measure with CCF. A small example is the function equality. Imagine that there are two players, each of them holds a k-bit string, and we want to know whether those strings are equal or not. So this function can be trivially computed by having player 1 send all his k-bits to player 2, and then player 2 can see whether the strings are equal or not, and he sends back 1 bit which says equal or not equal. So we know the output, and it takes only k plus 1 bit. And we can show that this trivial protocol is also optimal, but we won't get to it. But we won't show it. And a basic fact in communication complexity is that the communication complexity of each function is at least the log of its image. And the intuition for this fact is that just specifying the outputs takes log z bits. So you cannot do better than this. And the functions we are interested at are called social choice functions. And those are functions where the private value of each player is another function that expresses how much the player values each alternative. And since, as we've said, the private value of each player expresses how much he wants each alternative, computing the function might not be straightforward because players might misreport their values in order to get alternatives that they want more. And in order to handle this issue, we add payments. Okay, so we call a function implementable if for every player, if you fix the valuations for all the other players, the player always maximizes his profit by bidding his true value and not some other value. And in this case, we say that the payments P1 to Pn implement the function f. And we call a function combined with the payment scheme for all the players a mechanism. And we say that the mechanism is truthful if P1 to Pn implement the function f. Okay. So for every function, we use the following notation to denote the communication complexity of computing the alternative and the payments for it. And let's take a look at a small example of a second prize auction where the players are Pikachu, Ash, and Misty. So the communication complexity of the function is the communication complexity of saying that Pikachu is the winner because he has the highest value. And the communication complexity of the function and its payment is computing the name of Pikachu and saying that he also pays 20, which is the second highest bid. Okay, so our main question is how large can be the gap between computing a function and computing a function with its payments? And this is the question that we're going to try to answer. Are there any questions about the setting so far? Okay, so let's talk a little bit about the motivation for the question. We are interested in the question because it is often the case that we investigate the power of efficient implementable functions and pay less attention to their payments, where this approach is motivated by two kinds of results. The first one is that there are many important domains where you can determine whether a function is implementable or not without finding explicit payments for it. For example, in single parameter domains, all monotone functions are implementable, and in convex multi-parameter domains, all functions that satisfy weak monotonicity are truthfully implementable. And the second kind of results is that in many settings, functions have a unique payment scheme that implements them. For example, implementable functions whose domain is a connected set or a scalable domain satisfy this property. And these two kinds of results support the prices do not matter approach under the assumption that you get the prices for free when computing the function. And in this work, we investigate this assumption. Okay, so we'll talk a little bit about prior work. Fadel and Segal, who have also raised the question, have shown that the overhead of computing payments is at most exponential. And they have also shown an example where the overhead is at least 1 bit. And afterwards, Babayev, Blum-Rose, and Orange-Shapira have shown that there exists a function where all its normalized mechanisms satisfy that there is an overhead which is multiplicated in the number of players. And by the way, normalized mechanisms are mechanisms where bidding 0 guarantees that you pay 0. Okay, so our contribution is that we solve the question raised by Fadel and Segal by providing explicit functions with exponential overhead between the function and its payments. And we stressed that we do so for all the mechanisms, also for non-normalized ones. Our first result is that we show that even in two-player settings, where each player holds a scalar, there exists a function with exponential overhead. But one aspect that we like less about this lower bound is that it is based on a huge number of payments. But we showed that it was essential for 2 players. I'm going to explain this result and why it means that a huge number of payments was essential later. And we showed that if you add one more player, you get that there exists a function with relatively small number of payments, but that the overhead is still exponential for it. And one issue with both the functions is that they are a bit unnatural and contrived. So this is why we show that we can reproduce the exponential overhead in a more natural setting, which is a function that maximizes the social welfare objective in an auction. And we stress that there are 2 sources of hardness. The first one is the number of payments, and the second one is the interaction between players. Okay. We also provide some upper bounds. For example, for deterministic implementations, we show that if you include in also the number of alternatives, then you get a polynomial algorithm for payments, which takes a polynomial factor of the number of players, the number of alternatives, and the communication complexity of the function for all single parameter settings, and also for convex domains and functions that satisfy uniqueness of payments. And we also show that if we compromise on truthful and expectation mechanisms, then we get relatively efficient algorithms for single parameter and convex domains. And combined with
Can I ask a question? Can I ask a question?
Yes, sure.
I'm sorry, I'm trying to grasp what's going on. If the communication is supposed to be pairwise, right? Because if the communication would
What do you mean by pairwise?
Okay, so let me ask the question. I may be confused. So if the communication is public, which means that everybody is told what the allocation is, does this help? Or
we assume that everybody sees all the bits sent by the other players. It is the blackboard model, and also we want all the players to know at the end what is the alternative chosen. Does this answer your question?
So all the messages are public?
Yes.
both what the players are sending to, let's say there is a center or something, and what the center
There is no
says.
center. We assume that there is no center.
But okay, so suppose there was a center. Would that help? Would that change the question?
It wouldn't change anything.
Okay, so let's suppose there is a center, just for the sake of argument. I'm trying I'm confused about something, so I'm trying to clear it up. Okay. Sorry. So if everybody sends, I see, but they do not send the full VI. They send some in a low complexity communication complexity protocol. They send much less than the full VI. That's the reason that they cannot compute the payments by the rule that determines payments from the V's, right? That's the issue.
Yes, they send, there is a protocol for the function where they send the least number of bits possible. And then we see how we want to understand the gap of how many bits do you need for the function.
So that's why there is an issue. That's where the issue arises, because in an optimal protocol, you succeed in doing with sending much less than the full content of VI.
Yes, exactly.
Okay, I think that clarifies it. Okay, thanks. Sorry.
No, it's okay. Okay. So we showed that for truthful and expectation mechanisms, we managed to get relatively efficient protocols for single parameter and convex domains. And therefore, we get an exponential gap between deterministic implementations and truthful and expectation implementations. So this is our plan for today. First, we'll introduce some single parameter formalities. Then we'll show hardness via the number of payments and a tight characterization of the communication complexity of implementing functions for settings with 2 players. Then we'll see a proof of hardness via interaction. And I'm not sure we're going to have time for this, but we'll also see a truthful in expectation mechanism with communication complexity, which is polynomial in the number of players and in the communication complexity of the function alone. So intuitively, single parameter settings are settings where are relatively simple settings. More formally, those are settings where the evaluation function of each player has 2 components: a public function, which maps the alternatives to the reals, and a private scalar, where the value of each player is the scalar multiplied by the value of the public function. Let's see some small example. Assume that the auction is a 2-item multi-unit auction with additive valuations, and so the alternatives are who wins the first item and who wins the second item. So using this kind of single parameter evaluations, we managed to express that the value of each player for winning 0 items is 0, for winning 1 item it's Ri, and for winning 2 items it's 2 multiplied by Ri. Okay. So now let's formally define 2 properties of single parameter mechanisms. First, we say that the function is monotone if it satisfies that the higher I bid, I get an alternative that I want more. And second of all, we say that the mechanism is normalized if bidding 0 guarantees a payment of 0. Okay, and let's see a small observation that we are going to use later. If a function is implementable, then the evaluations of all the other players induces the following allocation graph for it, where the x-axis is the scalar that player I holds, and the y-axis is the value of the public function of player I whenever she bids Ri. And note that this graph is necessarily monotone because it is known that in single parameter domains, implementability and monotonicity are equivalent. But it does not necessarily look like this. In case it might also be like this or in any other way. This graph is just for illustration. So let's see a small example. If player I holds the scalar 4, it means that this is where his value falls. So the public function outputs 2, and its value for the alternative chosen is 4 multiplied by 2, which is 8. Okay, So according to Meyerson lemma, a single parameter social choice function is implementable if and only if it is monotone, as we've said before. And also, if the domain of player I is an interval, then the unique payment is given by this formula, which has two terms in it. The first term is actually the value of the player whenever she feeds this value. And the second expression is the area under the curve for the allocation graph between 0 and the scalar that she holds. But the allocation graph is this graph, I just remind you. Okay, so now we're ready to prove the very first theorem. And it says that there exists a social choice function between two players where the overhead of computing payments is exponential. So we named the two players Alice and Bob, and the sets of alternatives is 0 to k. And the domain is of Alice is such that her private value is taken from the interval 0 to k. And her public function is increasing very rapidly. She prefers alternative 2 much more than she prefers alternative 1, and she prefers alternative 1 much more than she prefers alternative 0, and so on. And Bob's domain is such that it doesn't care which alternative is chosen. He holds some private value, which is his value for all the alternatives. For example, if RB is equal to 1, then his value for all alternatives is 1. If he holds the scalar 2, then his value for all alternatives is 2. So basically, this is how we express his value. And note that since the size of the alternatives is k, and we get that the size of the valuation set is exponential in k.
Sorry, that was too quick. Can you go again over Bob's function? I didn't follow. Can you repeat? Can you go back?
Can I repeat what?
Bob's valuation.
Okay, so Bob's valuation, it's just, what it means is that it doesn't care. It doesn't care, no matter what is his value, he always doesn't care about which alternative is chosen. Imagine that it is just, if is the, wait a minute. If RB is equal to 1, okay, it means that his value for alternative 1 is 1, his value for alternative 2 is 2, is 1 also, his value for alternative 3 is 1 also, and so on, okay? And if RB is equal to 2, then his value for alternative 1 is 2, his value for alternative 2 is 2, and so on for all the alternatives.
I see. So he has a constant value for all alternatives, and that constant is chosen in this range. Do I understand correctly?
Yeah. The constant is his private value, but it is always constant.
Okay. And why is that k plus a? What is that? Where does this come from? I'm sorry.
What is
the k plus a minus 1 over a minus 1? Where does this come from?
I'm not sure what you're talking about.
The range of RB. The range of RB.
The range of RB. This is what I'm going to explain in the next slide. Where does this come from?
So, Shiri, I still don't completely understand the alternatives. We're talking about just allocating k items, or what are the alternatives here exactly?
Wait, who's talking?
It's Noam.
It's Noam. Okay, what did you ask? Sorry.
So, when you say the value for each alternative, am I correct in thinking, or did I miss a step, that the alternatives is just the number of items that he gets?
No, this is not the number of items. It is just
an abstract. It's an
abstract alternatives, but they are graded. There is always the least preferred, second least preferred, and so on.
For Alice, yes, it's 0 is the least preferred, 1 is more preferred, and so on. And for Bob, it is always constant.
It's always constant for each one of these alternatives.
Yeah.
So, I mean, can we think about these alternatives that are graded from the least preferred to the most preferred as having one more item each time, or is that not a good way to think about it?
Yeah, it's a good way to think about it. Actually, the result that I talked about with the welfare maximization, this is exactly what we do there.
Okay. So I can think about the alternative k, a third alternative I, as Alice gets I items and Bob gets k minus I items?
Yes, except that you need to think of Bob as You need to think that Bob doesn't care about the items at all. Only Alice cares about
whether he gets 0 or something, right? Or
yeah, he doesn't care about anything.
Okay.
Okay, so I'll continue.
So we can just think of Bob as having like, if the items are identical for him and his unit demand, for example.
Yeah, you can think about it this way.
But he's happy even with 0.
So you can increase, you can turn the 0 to be 1 and think about it this way. It doesn't matter.
And for Alice, what's the cardinality of A? Can you explain again the value of Alice?
The value of Alice is just exponentially increasing. It's increasing really, really fast. She wants alternative 1, much more than she wants alternative 0, and she wants, you can think about it.
So what's the size of A?
It is K. So
So
it's just, K.
But you did write, so it's K to the 4ik?
Yeah, K plus
K
1.
plus 1, K plus 1.
Sure, okay.
Okay.
Okay, thanks.
Okay, so let's continue. Okay. So as we've seen in the observation, each value of Bob induces an allocation graph for Alice. And the reason for it, we said that all the other players induce for each player an allocation graph. And in this case, we have only one. We have only one other player. And we construct the function f such that each value of Bob induces an allocation graph for Alice, where all the graphs satisfy 2 properties. First of all is that the allocation graph outputs the same values for each scalar and it's rounding down to the nearest integer. For example, f outputs the same alternative for 5 or 5.5 or 6 minus epsilon, and so on. And the second one is that whenever Alice holds the scalar k, she gets alternative k. And the number of such graphs is that satisfies those 2 properties is equal to the size of the valuation set of Bob, which relates to what Sergio asked before. And the reason for it is that we take the k plus 1 integers in the range of Alice's domain. We take 1 out because it is already matched with alternative k. And then this is the number of ways to monotonically partition the k remaining integers between the alternatives. Therefore, it allows us to construct a function such that each value of Bob induces a different allocation graph for Alice. And the proof idea is this. We say that each value of Bob induces a different allocation graph. And we see that a different allocation graph means a different payment. And since the communication complexity of the function is at least log the signs of its range, we get the needed result. This is just the idea. I'm going to talk more about it. So let's see a small illustration whenever k equals 2. So if Bob's value is just the all ones vector, then this is the allocation graph for Alice. It means that if she bits between 0 and 2, she gets alternative 0, and if she bits between 2 and 3, she gets alternative 2. Similarly, if Bob's bit is 2, then now when she bits between 1 to 2, she gets alternative 1. And note that each value of Bob induces a different allocation graph, and that all those graphs satisfy that every scalar was allocated to the same alternative as its nearest integer from below, and also that bidding 2 always guarantees getting 2. Yeah, and you can see it. Okay, so now let's formally prove it. First of all, the computation of f can be done in log k bits. And the reason for it is that it suffices for Alice to just send the integer, the nearest integer to a value, which takes log k bits. And then Alice can look at the allocation graph of this, see exactly where it falls, And then he sends back the alternative according to his allocation graph, and it takes also log k bits. Now we want to show that computing this payment requires at least k bits, where the payment is the normalized payment according to the Meyerson formula. First of all, as we've said before, the communication complexity of a function is at least the log of its range. And the valuation set of Bob is exponential in k. So it actually suffices to show that the range of this function is larger than the valuation set of Bob. So this is what we're going to prove. Okay. So let's fix two values of Bob and assume that Alice fits k, and we want to show that the payment differs if the value of Bob is VB or VB tag. Recall that we defined the function such that VB and VB tag induce different allocation graphs for Alice, and that her normalized payment is given by this formula, which includes her value for the alternative chosen, minus the area under the curve for the allocation graph. And here we just put in the scalar, which is equal to k, and the public function, and the value of the public function for k, and we get the area under the curve. And observe that we took the public function of k to be increasing fast enough, so different graphs have different areas under the curve, where the first term inside the payment is equal for all the values of Bob. So we get that we get different areas under the curve for different values of Bob, which implies that the payment is different for different values, which completes the proof of the claim. So let's sum up the proof. As I've said before, computing the function can be done in log k bits, and the range of this payment is at least the size of the valuation set of Bob. And it is exponential in k, which means that computing this payment requires at least k bits. But when we said before that we show hardness also for non-normalized payment schemes, and here we've shown hardness only for this normalized payment. So there is another lemma which says that computing this specific payment can be done by two calls to the most efficient mechanism for the function. So we get from the hardness of this payment the hardness of all mechanisms, and thus we complete the proof. And we won't show this lemma. Okay. As we've said in the beginning, there is one aspect of the proof that we like less, which is the fact that it has a lot of payments. This is where all the hardness comes from. And we now explain why we had no choice. In order to do so, we need to define the following notion, which means that if you fix the most efficient payment scheme for each player, then PF is the highest number of possible prices some player might pay for an alternative. In other words, it means that for each player, we go over all the alternatives, and for each alternative, we count how many different prices there is for this alternative, and then we take the maximum all the alternatives, and then we take the maximum over all the players, and this is this factor. And from now on, we're going to just call it the number of prices and not PF. And now we claim that the following characterization holds, that for every implementable two-player function, the communication complexity of implementing the function is completely determined by the communication complexity of the function and the log of the number of payments.
May I ask a question? Is it a good time to ask a question?
Yes.
I'm sorry, you say a lot of payments, and I think I've missed a step. When you say lots of payments, does it mean lots of function of payments? Because
when I said a lot of payments, I meant that the number of payments was exponential in k, And because of the fact that it was exponential in k, we showed a lower bound of k for the payment computation. And therefore, we managed to create the gap. Does this answer your question?
Like payment scenarios?
It means that
the range of payments.
The range of payments for each player.
For each alternative, there is an alternative. And for this alternative, you might pay different amounts. For example,
okay, so different outcomes of payments. This is what you're counting. Okay, thanks.
Okay. So now let's see the proof of the two-player characterization. Okay. So the first part is pretty trivial. First of all, implementing the function includes computing the function. So this inequality necessarily holds. And also, as we said before, a function is always larger than the log of its range. So this is how we get the second inequality. So we're done with this part. And in order to explain the other direction, we need to introduce the taxation principle. The taxation principle says that a truthful mechanism can be seen as a process where each player sees a menu with prices for all alternatives, where the menu is determined by the valuations for all the other players. And the output of the mechanism is an alternative that maximizes the value of the alternative minus the price of the alternatives for all the players at the same time. Okay. So now let's see a protocol for implementing the function, which means computing the function and the payments for both players. First of all, the players use the protocol of the function and get the alternative, and therefore they use CCF bits. And then then they both know the alternative chosen. And since the price of each player is determined by the alternative and the value of the other player, as we've said in the taxation principle, we get that each player knows the price of the other player. So they can just send it to each other using the log of the number of bits. Okay. So we're done with proving the characterization. Let's make some remarks about it. First of all, it has no assumptions at all. It holds also for multi-parameter settings. It holds for every possible function you could think of. Also, it is tight in the sense that you cannot remove any of those terms without getting a large gap between the communication complexity of implementing F and the remaining one. For example, if you remove the log of the number of payments, we've shown the exponential overhead between F and its implementation before. And also, you cannot remove the communication complexity of the function because then it is pretty easy to come up with a function where it has no payments at all, but computing the function still requires some computation. Also, this characterization justifies the fact that we used many payments because in two-player functions, the only way to get a large gap between this term and this term is to have the number of payments be doubly exponential in the communication complexity of the function.
Sorry, question. When you say tight, you mean you cannot drop any term, but it doesn't mean, for example, that you cannot make the two into one, for example. Is that correct?
Can you repeat, please?
Tight. What is your definition of tight here?
My definition of tight is that if you drop either the communication complexity of the function or the log of number of payments, you get an exponential. You can get an exponential gap between the remaining term and the term in here.
Okay, but it doesn't say, for example, that if you replace 2 log PF by log PF, the same holds, right? It just if you drop the whole term completely.
Yeah, it means that I cannot delete the whole term.
The whole term, but it doesn't say that the coefficient 2 is correct. Of the
yeah, but it's polynomial, so we care less about it.
Okay.
Okay. So the next question we're interested at is, can you make a function hard even though the number of payments is small? Which we show to be, and we show that there is such an example as written below. So now we want to prove that there exists such a function such that computing it requires log k bits, implementing it requires at least k bits, and the number of payments is relatively small in the sense that it is polynomial in k and not exponential in k. And this is the proof idea. It is that we want to create a situation where computing the alternative can be done locally with relatively few bits, but the payment computation is global. And keep this idea in mind by seeing the construction. Okay, so there are k+1 alternatives, and the evaluation set of Alice is such that a value for each alternative is the scalar that she holds multiplied by the alternative chosen. For example, if she holds the scalar 3 and alternative 3 is chosen, then her value for it is 9. And the values of Bob and Charlie are similar to the value of Bob before. They don't care which alternative is chosen, and they just hold an integer which says what is the constant value for all the valuations, for all the alternatives. And we mostly look at our values as k-bit strings, where we denote with VBJ the jth bit of the bit representation of Bob, and with VCJ the jth representation, the jth bit of Charlie's value. So this is how the function is described, and I'll explain it through an example. For example, if the value of Alice is 5.5, it means that only alternatives 6 and 5 can be chosen. So we look at the 5th bit of Bob and the 5th bit of Charlie, and if they are both equal to 1, we say that they intersect, and then alternative 6 is chosen. Otherwise, alternative 5 is chosen. So let's see how does F look like. Okay. We will do it by see an illustration for k equals 4. First of all, if the bits of Bob and Charlie do not intersect at all, this is their allocation graph that their values induce for Alice. It means that 0 for 0, 1 for 1, 2 for 2, and so on. If there is one intersection, it means that there is a bump at the location of this intersection. And if the intersection moves one place to the right, then the bump also moves one place to the right. And if there are two intersections, this is how the allocation graph looks like. So first of all, we're going to explain why computing F is easy, which means that it takes log k bits. Alice can just send the integer, the rounding down of her value to the nearest integer using log k bits. And then Bob and Charlie see what is the value of this specific bit that they hold. If it's equal to 1, everyone knows that this alternative is chosen, and otherwise everyone knows that this alternative is chosen. And now I'm going to need to explain the function disjointness. It is the canonical hard function of communication complexity, and it's a function that outputs 1 if x and y, which are k-bit strings, are disjoint, which means that there is no bit where their values are both equal to 1, and 0 otherwise. And disjointness, it is well known that disjointness requires at least k bits. So observe that even though computing the function was easy, the payment of Alice depends on the number of intersections. Therefore, we can reduce disjointness to the payment and therefore see that the payment is hard, because you can plug in x to be Bob's value and y to be Charlie's value, and then you get a certain payment for zero intersections, and a larger payment if there is an intersection. And also, the number of payments is always small. And the reason for it is that the payment is essentially equal to the area under the curve. And the area under the curve is unaffected by the location of the intersections. If you have an intersection in here, or an intersection in here, or an intersection in here, it doesn't matter. It always sums up to the same area under the curve. It is affected only by the number of intersections, not by their locations. And therefore, we get that the number of payments remains small. And observe that this situation is just the opposite of the situation that we've created for the other function. Over there, we created a situation where each small difference between two graphs immediately translated to a different payment. And in here, many different graphs converge to the same payment. Okay, so we are done with this proof. And so let's conclude what we've seen so far. We've seen the exponential lower bound based on the number of payments, a two-player characterization, and an exponential lower bound based on the hardness of the interaction between players. And those are all negative results. So let's see a positive one. Okay. So we remind that the mechanism is truthful in expectation if it satisfies that for every player. If you fix evaluations of the other players, the player maximizes his expected profit by bidding his true value and not some other value, where the expectation is taken over the random coins of the mechanism. And we denote with CC tie the communication complexity of the most efficient truthful in expectation mechanism for the function. And when I say efficient, I mean efficient in communication. And observe that the deterministic implementation is necessarily harder than implementation in expectation, because a deterministic implementation is also truthful in expectation. And one prominent downside of truthful in expectation mechanisms is that we expect that players are truthful only if they are risk neutral. If they are risk averse, they may want to misreport their values in order to reduce or eliminate the risk of a large payment. Okay, so this is the theorem that we want to prove. It says that if the private information of each player is taken from an interval, then a truthful and expectation mechanism can be computed by n+1 calls to the protocol of the function. And as we've said before, combined with our negative results, we get exponential gaps for single parameter functions between deterministic implementations and truthful and expectation implementations, because for the two constructions that we've seen, we showed that a deterministic implementation required a lot of bits, but a truthful and expectation implementation can be computed relatively easily. And we wanted to emphasize that the theorem holds also for convex domains. Okay, so now let's give the idea of the proof. Our goal is to output n random variables, where the expectation of each variable is this expression, which is the payment specified in the Myerson lemma. And how do we do it? First of all, we simulate the protocol of the function with v1 to vn. And then for each player, we get an unbiased estimator of the integral by sampling it at a uniform point between 0 and its scalar. And also, one obstacle that we need to overcome is that the players don't know the private value of each other because it is a communication problem. So in order to overcome this obstacle, we take for each type a similar type, which is based on the protocol of the function. And we show that it is enough to take the similar type. So, so we reached the end, and so.
Sorry, Moshe here. Can you go back? That was too fast for me. Like the last sentence. Can you say a little bit more? What does it mean?
Yeah. What we did is we looked at right. Each protocol is basically a tree, right? A binary tree. So you look at the leaf that V1 to Vn reaches, okay. And then you agree in advance on types for each leaf for all the players.
One possible types that will reach these leaves.
Yeah, leaf? Exactly. And okay. Then we take whenever we have RVI, that's in this expression we take the representative type. Okay. And because of the fact that they both reach the same leaf, we get that this expression is equal for both of them because of the taxation principle. If you could have reached the same alternative but get a different price, you would always want to get the lower one.
I see. Okay. Okay, thanks.
So what we've done is that we've shown hardness via the number of payments, hardness via interaction, and we've also shown hardness of welfare maximization. We've shown a two-player characterization, and we've shown some algorithms also for truthful and expectation implementations and also for deterministic implementations. And we also have a third kind of results that we are not going to talk about. So thank you.